Hello everyone. Okay, so first of all, let's try and understand that this session is going to be on the properties of numbers. We have almost completed the basic numbers module, and this is going to be a continuation of that. So properties of numbers. Exactly, the agenda today is that we will discuss something related to the square root of a negative one. A square root of a negative one is, this thing. I think you are going to be watching or looking at this thing for the first and the last time here only. This is from the areas of complex numbers. Okay, complex number as a topic has never been tested in the CAT, and you can be fairly confident that it will never get tested in the CAT. Okay, but then again, it's not very difficult as such. It's there in your higher school mathematics. What we are going to do, what we will be doing with this thing is that we will predict the squares and the cubes. We'll try and understand the pattern of the cyclicity of numbers with this thing. Okay, this will help us in a way building a bridge towards the remainder theorems and the basic remainder theorem, which is the cyclicity properties. What exactly is this term square root of negative 1 is called? If you must, this is called iota, and it is represented by the symbol I. That's it. You don't really need to know anything more than this. Now I is equals to square root of negative 1 is equals to I. This is the first iteration. Let's say if I want to square this number I square, what is it that I get? Obviously I'll get minus square root of minus 1 ka square, which will ideally give me a negative 1. Isn't it so? Okay. The third iteration is that I want to do, I'll multiply one more I into it, or I want to calculate for I cube. Just multiply an I to this term, you will get a negative I. You have to be careful. This is a negative I. I want to get to I square. I'm just seeing what all patterns I'm getting. I raised to the power 4 is nothing but, squaring this term, I square. That will give you a positive 1. Okay, please understand we are squaring. This is not a square root. Okay, so this is going to be a plus 1. Now, if you go to the fifth term, you will typically realize that an I will get multiplied to it, which is again an I. So exactly from here you can understand that the sequence will start repeating itself. In other words, if you see this entire sequence of numbers I raised to the power 2, I raised to the power 3, I raised to the power 4, they have a cyclicality. Some people also like to call this thing as cyclicity. Cyclicity you call it, or cyclicality of 4. Now what exactly the cyclicality of 4 means? That if there is a number, suppose given as I raised to the power 4k, I can predict the outcome. Let's take a number. Okay, let's take the number as, let's say I raised to the power 32. Can you predict what exactly will the result of I raised to the power 32 will be? Now, because I raised to the power 32 is a perfect multiple of this 4. Okay, so I can say that it will be nothing but 1. And how is that so? Because I raised to the power 32, let me use a different, I raised to the power 32 can be written as I raised to the power 4 into 32, or 32 into 4 also you can write, raised to the power 4 other you can say. And this thing invariably will give you nothing but a I raised to the power 4, which is a 1. Does this make sense? Okay, I hope it does. Now, let's do one more thing. Let's appreciate the fact that, okay, we need the cyclicity thing with us. So let's predict a couple of more numbers. Okay. What if the index of I is not a perfect multiple of 4? That is an interesting question. Let's try to figure that out. So suppose I have a number like this. Hold on. Suppose I have a number like this. I raised to the power 111. Now 111 is not a perfect multiple of 4. So what is it that I can do in that case? So I can possibly break 111, or let's say I divide 111 by 4, I get 3s are 12, so I can't do that. 2s are 8, I get a 3 1, so I get 7s are 28, and I get a 3 as a remainder. Now this 3 remainder typically means that I'll be looking at this part, okay, which is I cube, that is equals to minus I. Now if you have to predict what will be the value of I raised to the power 111, that will be equals to nothing but a minus I. Now please understand, I raised to the power 4 will have no remainder. I raised to the power 1 will have this thing. Okay, let's check for it. Let's say I want to check for I raised to the power 5 only. Let's do I raised to the power 5. Now if you like, I know you know it, but I just want to do it for the sake of simplicity. 4 1 the 4, remainder is 1. Ideally you should come to this number, but let's check anyways. This is going to be I raised to the power 4 into I raised to the power 4 over here is 1, and I is root over minus 1. That invariably gives me an I, and that is exactly what we predicted, right? So whenever you get remainder 1, this is the value that you will be taking. Let me take a different color, let's say to entertain this thing, let's take this one. So when you get a remainder 1, you will entertain with this value. When you get a remainder of 2, you will entertain this value. When you get a remainder 3, you will entertain this value. What happens when you have no remainder, which was in the case of I raised to the power 32? Now I raised to the power 32 happens to be a perfect multiple of 4, or 4 happens to be a factor of 32. In that case, you don't really need to worry, you just need to put this value, okay, I raised to the power 4. Let me elaborate on this a little bit so that you will be in a better position. Let's do one thing. Okay, so why the I raised to the power 4 is equivalent to I raised to the power 4k. Okay, I raised to the power 4k. Obviously you can see in the place of k you can substitute any natural number. You can put in k is 1, k is 2. In other words, you can actually write I raised to the power 4k plus 1 as the first remainder, which is going to be I itself. I raised to the power 4k plus 2, the second one, which is a negative one. I raised to the power 4k plus 3, which is the third one, that is a minus I. And I raised to the power 4k, that is a last iteration that gives you, hold on, let me check once, even I have forgotten the values. Yeah, that is 1. Yeah, so that is 1, right? So any number of the form 4k plus 1, 4k plus 2, 4k plus 3, 4k will give you the exact value of I in that iteration. I hope that made sense. We can actually play around with a couple of more numbers, but that's not actually required because I mean, this is the idea, the general idea. Acha, one more interesting thing that a student can think about, I don't know if you will ever go so much as to think about it, but somebody can think, sir, what happened, why not 4k I raised to the power 4k plus 4? Okay, why not like this? If you think like this, okay, if you want to think like this, if you're a non-engineer or somebody like that, or let's not say engineers, non-engineers, if you're just a curious person, because again this is not taught in the school days, what you need to do is, what you just take 4 common. When you take 4 common, you get k plus 1. Okay, now can I not replace k plus 1 as k dash? Just think on this. Can I not replace k plus 1 as k dash? Or I can maybe write it like 4j. So either it's a 4j or a 4k. What does it matter? It's a multiple of 4. It's a perfect multiple of 4. So any number like a 32 or a 64, or let's say depending upon, like, if it is a 4k or a 4k plus 1 or a 4k plus 2, we can deduce the values, right? So 64 also 4, let's say 8 will also be there, 16 will also be there, 20 will also be there. If you must check, let's check for I raised to the power 20. Okay, let me change the color. Yeah, so I raised to the power 20 can be written as I raised to the power 5 into 4. So, or you can also say I raised to the power 4 into 5. Okay, 4 into 5. 4 into 5, nothing. 4 into 5 plus 0. That inevitably will get you to 4k, that is 1. So the answer to that thing will be 1. If you have understood this, I would just say one thing. Just play around with it, because at the end of the day, you will have to ponder on this idea a little bit, because when we do remainders, this will be very much useful. Okay. All right. Now let's go to the next topic, which is the higher primes, or the seeds of the numbers. Again, a very interesting area for overall discussion. I don't think it's something to be something that we have to get worried about. So let's start. Let's name the topic. So all of you please give the heading. So divisibility rule of primes 7, 13, 17, 19, and so on. So basically we are looking at the higher primes. Okay. Okay. Now, this is an interesting idea that I'll be discussing with you all, so please pay attention. The property is a very interesting property. It's actually a very easy thing. You can remember it, and anytime you can deduce it. If you feel like you've forgotten about, if you feel like you forgot this rule, you can, you can deduce it on the spot. So we are going to use an idea of seed numbers. Okay. First of all, let us talk about what seed numbers are for a prime number like a 7 or a 13 or a 17 or a 19. Okay. I will also elaborate on where this seed number comes from, but again that is not required for cat, but just for the curiosity sake I'll give you the idea. So seed number basically is that number. Okay, so suppose I have this 7. So a number which when multiplied by 7, okay, please listen to this very carefully. A number which when divided by 7 should give me a number that ends in 9. Okay, that is not the seed number. This is not seed. This is not seed. This is where students make the mistake. Please listen to this. A number when divided by 7 when gives me the number that ends in a 9. So obviously that is 7. 7 sevens are 49. So this number plus 1 divided by 10 is the seed of a number. This is, if you see, 49 plus 1 is 50 by 10, that is 5. So 5 is the seed number of 7. Does this make sense? Now, if it made sense, great. If it didn't make sense, let's practice couple of more numbers. Like let's practice for, let's say 13. Let's practice for 13, because I'll do it over there. So 13 into a number that should give me a number that ends in 9. 13 threes are 39. Again, what is the algorithm? The algorithm is 39 plus 1 divided by 10. So this gives me nothing but a 4. Now this 4 is the seed number. Okay, let's do couple of more. Let us first of all calculate the seed numbers for a couple of numbers, and then we will understand how to use the seed number to predict the divisibility rule. Okay, so let's do for 17. I will also, go to the fact oscillator also, but again that is not important. 17 into something that will give me a number that ends in 9. Now if you pay attention, 17 sevens are 119. So it's not a 2-digit number, but I don't care. Algorithm remains the same. I add 1 to it, I divide by 10. This becomes 120 divide by a 10 gives me a seed of 12. So this is my seed. Okay, made sense? Now let's do one thing. Now that you have understood how to calculate the seed numbers for a couple of numbers, let's predict the divisibility rule. So the divisibility rule says, you can just look at this how I am doing it. Okay, so let's say I have a number 343 and I want to check for 7. How is it that I will check for 7? The rule says the last digit of the number that you are supposed to check, you will multiply that number with that seed number. So 34 and let's say plus 15, you will add this 3 5s are 15, you will add this to the first two numbers. Okay, we will always ignore the last number, we will multiply the seed to this number, and whatever number we get after multiplying the seed will add to the new number. So this is 9 and this becomes 49. Now straight away, because we were checking for 7, can you not see that 49 is actually divisible by 7? I should also tell you at this point that you should be aware that 343 is nothing but the 7 cube. Does this make sense? Now let's check one more number, 1001. Let's check this number for 7. For those of you who are aware of the concept of 1001, you should always know that 1001 is nothing but 7 into 11 into 13. Now this is a very interesting composite number that is designed by the product of the first couple of prime numbers, 7, 11 and 13. It's a beautiful number. There is a beautiful application of 1001 in subsequent lessons, but for this lesson itself I am just giving you the idea that let's check this number. Okay, so this can be written as 100 plus 05. So let's add 05 to this, so this becomes 01, 105. Let's do the thing again. 10 plus 5 5s are 25. This becomes 5 and a 35. If you see, 7 5s are 35. So 1001 is actually divisible by this 7. I hope that made sense. Now actually you can do this thing for all the numbers. Calculate the seed number and then you can proceed with predicting the divisibility. Is it important that you should always use seed number for predicting divisibility? I don't think so. You can like divide the number also in most of the cases, but this is an interesting idea for divisibility. If you want to keep this in check, you can keep this in check. Now let's go to one more interesting idea. I am just gonna give you the basic thought process of where this seed number comes from, because it's not relevant. I'm not teaching school kids. Even in school standards, these methods were not introduced because these are concepts of higher number theory. Don't waste your time. At the very onset, I'm telling you, don't waste your time. Your time is very precious. Time equals money. Don't waste your time. But then again, this is the ideas of osculators. A simple Google search will tell you what osculators are for numbers. Typically primes we are talking about. Okay, so what osculators tells us that you have seed, and with osculators you have this idea of a positive seed as well as a negative seed. Okay, so a negative seed, so a positive seed and a negative seed both are applicable in the case of an osculator. The idea or the theory basically says that any number, let's take 7 again as the number that we will use to calculate the oscillators for. 7 needs to be multiplied with a number such that it gives, ultimately I need to reach to 10, 20, 30, 40, 50. Okay, either I want to reach to a number which is 1 less than that. Okay, 1 less than that or 1 more than that. This is exactly what we did for the positive seed. If you pay attention, we worked out the entire theory that I gave you in the last part. That was for the positive seed, but now I'm giving you for the negative seed also. So let's just look at the negative seed only. So I want to reach till, let's say 7 1s are 7, so I cannot reach 10. I can reach 20 because 7 3s are 21. So 20 1. Now please pay attention. The theory for the negative seeds says that you subtract -1 from then, divide the 10, and you get a 20 by 10, giving you a negative seed of 2. Now the process remains exactly the same. Suppose you have a number 343. Let's take the number again. Okay, this is just to, feed to the curiosity of the students. Otherwise, not required. Yeah, so again 343, need to check for 7. Okay, check for 7. How exactly can we check? This time around we are not going to be, hold on, this time around we are not going to be looking at adding the number, but we will be subtracting. Okay, so this will be like this: 34 minus 3 into 2. Okay, don't write 3 into -2, it will be 3 into 2, because the negative seed is 2. So that becomes 34 minus 6. 34 minus 4 is 30, minus 2 is a 28. 7, we had to check for 7. So 7 4s are 28. So this is also an idea of this is also an idea that you can use to predict the seed of this number. Okay. Having said that, I would say stick to the positive seeds. Theory is very interesting. You just need to calculate for 9, and then you can do add 1, divide by 10, calculate the seed number, add, predict whether the number is divisible by the initial number or not. So I hope you enjoyed the session. If you did, you know the drill. There are courses that I'm running, CAT 24 courses for quantitative abilities as well as DILR. If you're interested, you can get in touch. Description mein you will have the details. Thank you.